is the energy levels are still discrete, but they're no longer equally spaced. And that allows us, if we tune our energies to h bar omega 0, we can focus on the two levels. So we've gone from an infinite ladder of equally spaced levels to practically two-level systems. And this is what people actually work on with these kinds of qubits. Now let's take a look at this. In order to maintain the discrete nature of a quantum system, we have to operate in an environment for which the thermal energy doesn't mix up the states. We have to make sure that we can operate either at the ground state, E0 or E1. And in terms of an effective temperature, defined through Boltzmann's constant, because kT is an energy, we find that since the typical energy of these Josephson junction qubits is on the order of gigahertz, using this frequency temperature relationship, that we need to operate at a temperature that's much, much colder than we might ordinarily think in order to maintain the quantum nature. We try to do it at room temperature, forget it. We try to do it at 4 Kelvin, forget it. So typically, since 10 gigahertz corresponds to half a Kelvin, these superconducting qubits have to operate in the milli-Kelvin range. And as you know, it's no mistake, that's really cold. It's a lot colder than outer space. If you're at the 3-degree background radiation, 3 degrees Kelvin, this is 1,000 times colder. Really cold. But this can be achieved in the lab. Amazing. So now we go from the qubit itself to what we can do with it. And it's important to be able to initialize and then manipulate, in this case with microwave radiation, at the same frequency as the energy level difference. And then ultimately to measure the qubit at the end of a computation to get an answer. And these three requirements, initialization, say make sure we start off in the ground state. In that case, we can just wait for thermodynamics to put us in the ground state, or spontaneous emission of a photon. And there are more sophisticated ways. But to manipulate the state of the qubit that we talked about, we need a time-dependent term in our energy, and that's furnished by the microwave pulses. And then ultimately to read it out, which we'll see. Now here you're looking at a brief glimpse, we'll see in more detail later, that the qubits look like microwave circuits. If you've seen that, they're resonators, they're control lines, and radiation can be pumped into that. But we'll see that in more detail later. And those are three of the criteria called the DiVincenzo criteria that has been proposed as requirements for any particular qubit modality. Not just Josephson junction. So here's a close-up of a transmon. It's called that because it's an X. If you rotate it 45 degrees, it looks like an X. The red is mostly a capacitor. The capacitor that's parallel with the Josephson junction inductor. The Josephson junction is actually down here in the little blue box. There's a separate wire passing a current that induces a magnetic field that allows you to tune the energy levels due to manufacturing tolerance issues. And then there's another microwave run that allows the propagation of pulses in order to change the state of the qubit. The qubit is then coupled to other qubits to entangle it. We'll see that in more detail. And then finally to a readout resonation. So here, zooming out on one of the Google chips, this Google wholesale hired the whole quantum department for UCSB. It's amazing what you can do with money. And the plus signs, or the X's, are the 5 different qubits. Each has a readout resonator, the squiggly lines. And there are microwave control lines for the current to tune the energy level spacing, as well as to drive the state transitions of each qubit individually. Now, rather than go through the details of yet another chip, and for the engineers in the audience, if there are any, it looks like a microwave design. And more the physicists now are realizing that now that they've got the basic science ironed out, what they really need to do is use some good engineering practice to make a good design to get the best performance out of the qubits. But this thing over here is where the qubits are placed. So actually at the bottom of what's called the dilution refrigerator. It's inside, it's nothing that you want to put your chicken in or anything for dinner, but it's a huge cylindrical contraption that often hangs from the next higher story in the lab. And it has multiple stages, and maybe starting from 77 Kelvin for liquid nitrogen, and then down to 4 Kelvin liquid helium, and then through complicated helium-3 and 4 interactions, you can actually cool the very bottom to the millikelvin range. Of course, this is sealed up inside that when the qubit is put in. But there are huge issues with all these microwave cables and control lines. It gets very, very complicated. And so since practical quantum computers will take thousands or millions of qubits, this is not a scalable solution. And so some kind of technical breakthrough is needed to make this practical. But at least for now, we can get working 53 or maybe 70 or so qubits and do some really good fundamental science and demonstrate computation. But there's definitely room for breakthrough. So we talked about the block sphere. The states can be anywhere. I want to show you a quick animation to understand how a microwave pulse at different phases will move the state around on the block sphere. There's a frame. So we're going to go, there's a pulse around the x-axis. We're rotating back around the axis, back to the ground state. Now around the y-axis, all the way down, and now a lower amplitude pulse takes us halfway there to the equator. And then another lower level pulse around the y-axis takes us back. The reason going halfway is important is because that puts us in an equal superposition. So we need to be able to put each qubit into a superposition, and this is how it's done. I can do that maybe again at the end. So we can make sure. It's important to note that the actual frequency of the microwave radiation is again tuned to the transition frequency or the energy level. That's all we're seeing again. This is called a pi pulse. Now a pi pulse shifted in phase around the other axis. Now a pi over 2 pulse, that's with respect to the spherical angles I talked about earlier. Now, another way of looking at what I just showed with animation is the top, or is this sequence here, but let's look at the line. It says qubit 1. This is the simplest kind of quantum circuit diagram. So in a quantum circuit diagram, there's a line for each qubit. There's a representation of its initial state, so I've used the ket 0 as we introduced before, or in terms of the components, a column vector 1 and 0. And then a particular pulse applied to the qubit in the way I just showed you is a quantum gate. It evolves the quantum state from the initial point on the top of the block sphere to wherever else the pulse takes you. So with a pi pulse that we just showed you, it takes you to the 1 state at the bottom. And if you do it again, it takes you back to the 0 state. So basically, because you're going from each state to the other one, it acts as a NOT gate, a classical logical operator on the qubit basis states. And the symbol is an X gate. It actually, for the X is actually related to the Pauli spin operator that generates rotations about the around the x-axis. And there's a matrix representation in terms of the column vectors that represents the linear transformation performed by this pulse. So quantum mechanics is linear. It's great. That's one of its great advantages. And to understand it, you need linear algebra, and that's pretty much it. So understanding qubits takes a little bit of work, but you don't need to study the partial differential equations. You do everything with linear algebra. Yes, I have a question in that.
Can you remind me what is going through all these different states? Are we talking about some fundamental particles, or
Now this is for example, let's think the spin a half. So we're changing the state of a particle that has a degree of freedom, in this case the spin, which is related to the symmetry of rotation of a quantum particle. So it's a type of angular momentum. Angular momentum has to do with rotation. When we manipulate the state, we are transforming the state consistent with that symmetry, in a sense.
Who is in that state? Are you talking about like electrons or somehow?
Yeah, so you can think of an electron, an isolated electron in a static magnetic field. There's a quantum state associated with the spin dynamic degree of freedom. That's what I'm talking about. When I put in a magnetic field in the x and y plane, and it varies in time, I am changing the state of the spin state of that system. It's a quantum particle. It has translational states, where the wave function, where it's located in space. It also has part of the wave function of a quantum particle is the spin. I'm talking about the spin degrees of freedom, the state of the spin, and how we translate or permute or change, perform a symmetry operation on that part of the quantum wave function. So it's still kind of abstract. You can think about the qubit. I mean, if you want a picture, the qubit is spinning, it's rotating at the frequency of the energy difference. That's another way to think about it. You can think about spin as a top that's moving at the frequency omega, where h bar omega is the energy difference. And the qubit is spinning, but now you're also trying to flip the spin, the vector that defines the state of the spin. Okay. And the point of this is that we have the x gate before that takes you from 0 to 1, but if you go halfway down, those lower amplitude pulses, you rotate this spin around the Bloch sphere, and we're now on the equator. And if you looked at the parameterization of the state, that puts you in an equal superposition of 0 and 1. And that's typically a starting point for any quantum algorithm. And that's a square root. You can take an arbitrary, then you have all this continuous infinity of variety of these gates, depending on the amplitude and the time duration. If the pulse is out of phase by 90 degrees with respect to the rotational frequency, you rotate around a different axis. And these are the degrees of freedom that the scientist employs specifically to achieve an arbitrary rotation from any point on the Bloch sphere to any other point. So that's kind of the idea. And here's a typical experiment that's done when a new qubit chip comes back and the scientists want to make sure it's working properly. They will take their qubit and then they will apply a pulse, but instead of stopping at a certain amount, they'll keep evolving it. But they choose first a time interval that's very short. They apply a short pulse and they make a measurement. And remember, when you make a measurement of the qubit, you'll get a 0 or 1. But if you start at 0 and you make the measurement very short thereafter, the probability that it's going to be a 1 is very low. So the red dots are kind of obscured by the axis. They start at 0. So for very short time, the probability of getting a 1 is small. But as the pulse increases, as we've seen, a full pi pulse will give us a high probability of measuring the state in the 1 state. Now, every dot there is 1,000 measurements average, because all we can do is get the probability. That's quantum mechanics. But if you take enough measurements, you start over again, you take 1,000 measurements, then you increase the time, take another 1,000 measurements, you can calculate the probability. If your qubits are behaving properly, you'll get this nice oscillation named after Lab-Rabi, the Nobel Prize winning physicist. So that's the theory. In practice, you observe this because the qubits are so sensitive to the environment that the superposition that you put them in is very fragile. So thermal energy can destroy the superposition. If you started in a 1 state, you might fall to the ground state, given thermodynamics. So there's in reality a very short time over which you can manipulate the qubit coherently. And so the key to doing quantum computations is to be able to make enough gates to do what you want before the qubit decoheres. And these time scales are also the same as magnetic resonance. Yes?
Yeah, because the temperature isn't really zero.
Temperature not being really zero is one of them. Others are stray electromagnetic radiation. When you put a pulse on, you affect other qubits. The material defects actually are quantum mechanical defects, and they interact with the qubits. There could be, so there's all kinds of electromagnetic interference as well as temperature. So all kinds of things come in. Qubits are super sensitive. So that's a good question. All right, so they typically last, these kind of qubits last only about 200 microseconds. The question is how many good quantum gates can you manipulate to do a computation. Okay, I want to talk about entanglement since that's really key for quantum algorithms. So we talked about one qubit being in superposition. Now we're talking about a system of two qubits. So two qubits live in a 2 squared or 4-dimensional space. And so the state of a 2-qubit system is just a linear superposition of its basis states. You can enumerate the basis states in terms of all of 2 bits, 0, 0 to 1, 1. That's 4. And if we take a particular example of a 2-qubit state where, say, C1 and C3 are 1 and the other coefficients are 0, we get the state on the left there, 0, 0 plus 1, 0. Since the second qubit has a 0 in both cases, we can kind of factor it out. And what that means is that in this state, qubit 1 has a definite state. It's a definite superposition, equally 0 and 1, the same magnitude, square root 2. And the second qubit is definitely in state 0. Now that kind of state is not very interesting. What's really interesting, though, is if you take a state with C1 being 1 and C4 being 1, that's called an entangled state. That happens to be one of the Bell states, of which there are 4. It's super correlated beyond anything that's even possible classically. And some other time I can explain that. But the key thing is it's still a superposition. So if we were to measure, say, one of the qubits, let's say the first qubit, we would collapse the superposition. We learned about that earlier. And if we measure one of the qubits and it comes up 0, we know that we collapse the superposition into the 0, 0 state, which means the second qubit has to be in state 0. So without even measuring it, we know the second qubit that we didn't measure must yield a result of measurement that's the same as the first. And likewise, if we were to measure the first qubit, we got a 1, we'd know that the state collapsed into this, and we can see from the coefficients, either of those results, it happens with equal probability. Yes, please.
So how good are we in the lab at making like really a perfectly exactly entangled Bell pair?
We're pretty good at it. Yeah, you can get Bell states with like a 99.8% fidelity, and usually making Bell states is a prerequisite for doing anything useful. So that's a good question. But another thing about entanglement is, again, we have 2 qubits. They're 2 physically distinct particles. They're spins in a magnetic field. You can look at each of them separately, but if you prepare them in a state like this, and then you send one of them off in a rocket ship across the universe, and you measure your qubit the same way we talked about, whatever result you get, you know with certainty instantaneously that this person over here must measure the same value that you got when you made your measurement. Now you can't send that information to them faster than the speed of light. You're not causing that. But when you compare notes later, when you send light signals or when you go back, when he comes back from his vacation, you can compare notes and there's 100% correlation, or 99.9% correlation. And entanglement is what's needed. That's what's new about systems. And you get entanglement with 2 or more qubits, yes.
Is this an ideal sort of situation? Because with the other diagram you showed us, with the oscillation, that
Yes.
was the ideal form of what you're going to get. So how can you assume that one qubit is going to have a certain value if it's always going to be changing because of quantum?
Okay, that's a good question. That's a very good question. So if in the oscillations, before they started to decay, if you do them, say over the first cycle or two, you can get within 99.99% accuracy that the qubit's going to behave as theory says. And there have been lots of experiments demonstrating this kind of correlation when you make the measurement and you compare it. But yes, if you leave a qubit alone, it's going to change. But once an interaction with the environment happens, whether it's a measurement or an even advertent interaction with the environment, the qubit is not a qubit anymore. It doesn't have a coherent state anymore. It's not, the superposition is gone. So it doesn't behave as a qubit. But you're right, to do anything useful, you have to continuously refresh the qubit. You have to then put it back in a state and then re-manipulate it. So that's a good question. Okay, so we talked about entanglement. It takes 2 or more qubits. We go to 3 qubits, it's 2 to the 3. So the point is that, and that's 8, of course. When you have n qubits, the size of the quantum mechanical space is 2 to the n. And people estimate that there are only 10 to the 80th particles in the universe. If you solve this equation, that says that there are more states in the superposition of less than 300 qubits than there are atoms in the universe. And you can roughly argue then that if every atom in the universe were dedicated to classical computation, you could do as much with 270 ideal qubits. That's a little bit of a stretch, but that shows you how dramatically powerful the quantum paradigm is because of the exponential scaling of composite quantum systems. When you add a new component to a quantum system, you double the space of the size of the space. And I want to make, well, let me come up here. Now, so now that we have 2 particles, we need a 2-particle manipulation. We talked about the single qubits, which we can visualize in a block sphere. Once we get to 2 and they're entangled, you really can't visualize it. There's no good picture, at least that I understand. But one can simply represent the matrix. We saw, say in the lower right, the NOT gate is just a very simple matrix of 0 1s that flips the basis state. And when we get to 2 qubits, here's a gate that allows us to entangle qubits, and it simply permutes the 3rd and 4th basis element. And it is a controlled X gate, or a controlled NOT gate. The NOT part is at the bottom right, and it says it will change the bit of the 2nd qubit conditional on the 1st bit being 1. So that couples the degrees of freedom, and at least mathematically that allows us to represent the action of this entangling or controlled NOT gate. So here is a quantum circuit with the symbol of the controlled NOT gate, and X and Y then can be 0 or 1. And this is addition modulo 2. So if I put 1 and 1 here, I get 1 and 0 here. And if you look at this, this is just the exclusive OR gate from classical logic. But classical logic is usually not reversible. Quantum mechanics, these linear operators, not only are they linear, but if they're evolution operators, they have to be so-called unitary. They have another symmetry. The conjugate transpose is the inverse. So any quantum transformation of changing the state, like I talked about, can be undone, and you can reverse it. Now, fortunately, it turns out that classical logic can be augmented. So the exclusive OR gate, if you keep one of the inputs, is reversible. So as an exercise, do this again, and you'll see you get the original inputs. And so the first step in quantum algorithm is to take the classical logical function you want to implement it in a reversible way. This gate in terms of its mathematical definition, it doesn't tell you anything about quantum mechanics. But then you implement it with a linear operator, just a matrix, and then you have to figure out how to implement that matrix in terms of pulses. That's a little bit too complicated for this lecture. And, okay, that's what I said here. But the theorem is, given all the single qubit rotations on the Bloch's field, that and only this one additional 2-qubit operation together are enough to perform any quantum transformation on the n-dimensional space of n qubits. So that's a very powerful fact, and it means these are your basic building blocks for any quantum algorithm. That's called the universal gate set. And just quickly, we're going to take 2 qubits, we're going to start them in the 0 state. We're going to put them in a superposition with a slightly different matrix. Again, any box that applies on one line transforms only that qubit. So if I transform it, it puts the top qubit in an equal superposition of the 2 basis states. The composite state factors, because this is the same state we met before when we talked about entanglement. Now we apply the controlled knot gate by linearity, one of the great virtues of quantum mechanics. It won't do anything to the first one because it will only permute the second bit if the first bit is 1. So it leaves that alone. But when it acts on this part, it will change the second from a 0 to a 1, and lo and behold, we have a Bell state. So this is how you generate entanglement from 2 qubits. And the key thing here is very interesting. The maximal amount of information you can know about a 2-qubit system is contained in the quantum state, but there is absolutely no information contained in this state about the individual components of the system. Qubit 1 is not in a state. There is no quantum state that represents qubit 1. There is no quantum state that represents the state of qubit 2. It's a 2-qubit state, but no information is there about each state. That's not the case here. Before that, each qubit is in a definite state, as we talked about. That's the difference between entangled and non-entangled state. And then when we measure it, we went through that. So we now get to readout briefly. So we do algorithms, we manipulate states like this, we entangle qubits and have them interact with pulses, and then we have to get an answer out. So what we do is we couple a microwave resonator, we could say capacitively in this technology, to the qubits, which are these oscillators, and we inject a microwave signal into this coupled system. The readout resonator is typically designed to have a frequency that's about a gigahertz higher in frequency than the typical 10 gigahertz qubit frequency that we talked about. And that provides a coupling that enables this kind of detection. So the signal comes down, interacts with the resonator that's coupled with the qubit, it goes back up and comes out as this B2 wave. This is a microwave measurement. It's a scattering measurement. It's an S parameter measurement. That's what S11 is. And the amazing thing is that the coupling between the qubit and the resonator shifts the resonant frequency of the resonator from whatever it is, say gigahertz, plus and minus, depending on the state of the qubit. It's really remarkable. It's like a capacitor where the dielectric constant depends on the material. So you can tell what material you have by the dielectric constant. So that's kind of an analogy. So you can measure either the phase shift or the shift of the resonant dip in the transmission of a microwave signal through this coupling. And there's actually an analogy with the interaction between the resonator, which quantum mechanically is photons, and the qubit. It's like the Lamb shift in quantum electrodynamics that won the Nobel Prize in the early part of the last century. Okay, quantum algorithms. The key for some of these algorithms is that it's not just probability, which we talked about, but the fact that in quantum mechanics, the amplitudes, the quantum the probability amplitudes are even a more fundamental concept. The amplitudes for two mutually exclusive events add, and the probability is the absolute square of the sum of the amplitude. So classically, if you have two ways in which an event can happen and they're mutually exclusive, the probability of having the event is the sum. But quantum mechanically, it's the amplitudes that add, and so when you calculate the probability, you get the classical result, but there's a new term. The amplitudes interfere, like vector fields, like electromagnetic fields. They interfere based on the relative phases of the amplitude, which is the more powerful concept. Quantum interference, and that's the basis of the double slit. So go read Feynman's first lecture in his quantum mechanics to understand it. And I love this quote. You know, if you have one way that an event can happen and you give it another way, it may happen that the event can't happen at all due to quantum interference, destructive. But maybe you can try to do constructive interference. Then you can enhance the probability of an event that you may want to happen. And that's the basis of a quantum algorithm. I think I'm taking it for this slide. So we start the input for the algorithm in an equal superposition of all the possible states. There are 3 qubits, so there are 8 states. I'm only showing 4 of them here. So by simple rotations on each qubit, we can get a superposition. Then we start exercising the set of qubits with single qubit gates. That's the thin lines. Only one qubit is being manipulated. And think of the probability amplitude waves diffusing and interfering with each other, maximum and minimum. Then we do some of the 2 qubit gates related to the controlled NOT gate and other cousins of that. And then the probability amplitudes interfere, like waves again. And the genius of the people who've come up with these algorithms are that if for the particular problem, you can somehow figure out what gates to apply in this evolution, you want the answer to come out as the only amplitude that has a large coefficient close to 1 and all the other wrong answers to have a small amplitude. So that when you make a measurement, which over here, if I made a measurement, I have equal probability of getting every possible answer that my discrete system can give me. Here, if this is the right answer, I want to make a measurement and have a very high probability of getting it. Yes?
Are these probability amplitudes real, or are they mathematical?
Oh, very good question. That's been a raging debate for 100 years. So I'd certainly say they're mathematical, and in a joke, they're not real, they're complex. That's why they interfere. So you need complex arithmetic. Some people will say, oh, what, you know, is the wave function real? Oh, I don't know. But it certainly is the required machinery. It's what the Schrodinger equation gives you.
So you have to factor it in.
You have to deal with the amplitude. In any experiment, you have to calculate the amplitude. You have to solve the Schrodinger equation. And I should point out, when this is going on, you have to shut the door and don't look. You don't want to bring a light with you. You can't monitor the process because you'll destroy this coherent evolution. The Schrodinger equation is deterministic. Yes, we talked about probability in quantum mechanics. The Schrodinger equation is a linear partial differential equation. You know the state at time 0. You solve the Schrodinger equation, the time-dependent version. You'll get the state at any time if you can only solve it. And this is the physical way of realizing it. But when you make a measurement, you collapse the state and you get whatever you get according to the probability distribution, which comes from the wave function that you solve with the Schrodinger equation. The Schrodinger equation is deterministic. It's complex value, and it's, you know, the great scientists of our age and before have struggled with this. It's a good fundamental concept. Okay, and so here's another circuit diagram. We're getting more complicated. Any real algorithm has many qubits. There are single qubit gates. There are any pair of lines that are connected with vertical lines or boxes with 2 qubit gates. Effectively, cousins of the controlled NOT gate. And in the end, to affect these transformations, you apply microwave pulses of different amplitudes and durations and frequencies, and then these are biased pulses that will maybe modulate the energy levels of the different qubits. We talked about challenges, the temperature environment, the multiple cables, the high error rates. It sounds, 99.9%, pretty good, but if we think about it, what I've heard is that classical transistors have an error rate of 1 part in 10 to the 14. So we don't really need redundancies. But to do anything reasonable, even 1 part in 10 to the 4th means we can only do 1,000 operations until we absolutely have an error, and that screws things up. So we have to push the error threshold down and then be able to mitigate it with things like quantum error correction. That's the next one. And to correct errors, we use the general principle of redundancy, and that applies to classical systems as well. So let's say we replace a single qubit with a set of 3 qubits. And 3 qubits live in 8 dimensions, but we want a 2-dimensional subspace, so we can do a logical 0 and a logical 1. So we take 0, 0, 0 as a logical 0, and 1, 1, 1 to be a state which would be logical 1. So that means if we put qubits all in the same state, in one of the states that's the logical 0, and all in the other state that's the logical 1. Only 2 of them, and then we operate on the group of 3 qubits. Now, if we were to detect a 101 or a 001, we know we have an error because we're outside of that subspace. We don't get one of those 2 basis states, and therefore we have to correct it. And the simplest scheme of that is, well, the error rates are relatively low, so whichever is the odd one will flip the bit. So that's the idea. And roughly, it can be implemented this way conceptually. So we have our 3 data qubits making up 1 logical qubit, and then we use entanglement. But now we entangle 2 additional qubits, 1 each, with pairs of the physical qubits. And remarkably, we can then measure the entangled qubit and make an inference about whether or not a qubit has an error and which qubit has an error, without measuring the qubit. Remember, we can't measure the qubit, we destroy the information. So we have to do something really clever. I shouldn't say that. We need a parity. We need to check that the qubits have the same value. And we can do it by taking 2 measurements. There are only 4 possibilities. And depending on what two-digit binary number we get, we know which qubit had an error, and then we actually know how to correct it with what particular microwave pulse. So that's how we do it, but we have to do it quickly. We have to be able to do the entanglement. We have to be able to do the measurement. We have to be able to make a decision based on the measurement what new pulses to send out to make the correction. That's why we need real-time, highly synchronized
Well,
systems.
I'll wait for questions.
Okay. All right. So actually, that's what I said there. So I think that's it. Oh, just so now the state is such that we typically require like 1,000, a redundancy factor of 1,000. So we're nowhere near practicality, but it's coming down. There is a threshold. There was actually a paper recently, I forgot which group, that claims, I think it was the Google group, that they have demonstrated scalable algorithm where they're showing that they've got the error down enough to prove that they can get more benefit from the redundancy and quantum error correction than they're losing with these error rates, which is really quite remarkable. Okay, so let's summarize. Yes, it's a fantastic idea. Lots of people doubted it would ever be real. The science, though, is unassailable. The basic physics of quantum mechanics, nobody's argued with. It's whether it can become practical or not. But there's clear progress. There's very significant practical work. Good old microwave engineering can be a key to some of the technologies. Many of them, we already talked about superconductors for spin and silicon. And there's a new discipline that's arising. It's a subdiscipline now, sometimes it's called quantum engineering. So groups like MIT and other major players around the world are beginning to build curriculum, master's level programs, where they're introducing quantum mechanics, as I said, through the linear algebra and some practical microwave engineering, and they're getting the physicists to work as designers and understand that. Merging the language, having these people talk to each other, we have eminent physicists come up who don't know how to get a signal into a chip to reflect all their power. So there's enormous opportunity for cross-fertilization, and it's a tremendously exciting time. So if you're interested in physics, this is a great opportunity. So I wonder, I guess Lynn left, but here's the updated Google search from January. Would anybody do it from today? Is it any different? I don't know. Anyway, I think I'll leave it there. I'm happy to take questions later.